Can you hear me? Hello.
Yes, sir.
Okay. So let's start. It is our first tutorial. So I'm Bittu Singh from IIT Bombay. I'll take tutorial of this subject, essential of topology.
Excuse me, sir.
Yeah.
Is this supposed to be something of one-to-one meeting? I don't see any other students.
There will be less student. I don't know if there are other students.
Okay, sir.
So before that, what is topology? So we already familiar with real analysis. We have real number R, and there we can study those kind of open sets. Open sets, it's like union of those kind of open interval. So it's some kind of this union. We define open set in this way. So a set U is open if there exists. So for all A belongs to U, there exists a neighborhood. A neighborhood means open ball. An open ball. For example, A minus epsilon to A plus epsilon. Those kind of open ball which contains A, and this open ball, let me denote it by B epsilon. This B epsilon should containing U. If this hold for all A belongs to U, we call it open sets. So those kind of ideas transferred to those metric space. Metric space is similar kind of thing. We define a metric D. So given a set X be a set, and we define a metric. It takes two values and it sends to R plus, which is positive non-negative real number, and it satisfies those kind of property. So d of x comma y, so distance between two things should be non-negative, and moreover distance is 0. This is true if and only if x and y are the same point, and it also satisfies those kind of symmetry. D of xy is same as d of yx. Moreover, it satisfies those kind of triangle inequality. D of xy, d of plus d of yz greater or equal to d of xz. Triangle inequality. So this is called metric space. Now these ideas can be generalized further. So here in metric space, the open balls are defined in a similar manner. So instead of uh, those kind of neighborhood, now the open ball, it will look like this. So open ball in metric space is defined like this. So B A comma R, we are taking a metric space X comma D, and here the open ball, and take A belongs to A be a point of this space X, and R be any non-zero number, real number. Then this open ball, it is defined by all X belongs to X such that distance from A, this is less than R. So this set is open ball. For example, in R2 with standard metric, open ball around 0 of radius 1, it will look like this. This distance is 1 and the point, this is 0 comma 0. So precisely this 0 should be written as this 0 comma 0, this point. This is the origin O. So this is the open ball. Everything inside this. And similarly, if we define the metric, so again consider R2 and define the distance like this. distance between 2 point x comma y. Suppose x is this point x1 comma x2 and y is this point y1 comma y2. Define this distance by mod of x1 minus y1 plus mod of x2 minus y2. So in this case, what will be the open wall? B0. So again, 0 denotes the origin, 0 comma 0, this point, and radius is 1. So what will be this open wall? Let me draw a picture. Suppose this is 1, and similarly this will be minus 1. That is minus 1 comma 0 in R2, 0 comma 1. Sorry. Okay. In this case, so we can put, suppose x. So suppose this is our a, and now we want to find those kind of x, right? So x belongs to this, x belongs to b01. That will imply d of x comma this a means the origin, this should be less than 1. This is if and only by definition. Now if we put the value of a is 0 comma 0, then this is x1 minus y1. Instead of y1 we have a1, which is 0, plus x2 minus 0. This is strictly less than 1. So that is same as saying x1 mod x1 plus mod x2 strictly less than 1. And that area, actually that area can be drawn like this. So you can see this line is x1 plus x2 equal to 1. So all those points are in the open wall. Similarly, because there are mod, we can replace by minus x1, we'll get the same value. So this dotted area will be, so we need to remove those kind of points. Those points will be not there. Those boundary will be not there. So this is the open wall in this metric example. Okay. Now those kind of continuity and all those results, whatever you have earlier seen in real analysis or metric space, those areas can be generalized. So in metric there are some notion of distance, but in general there may not be those kind of structure, those kind of addition, multiplication, and those kind of distance may not be there. Then also the whole thing can be studied in terms of sets function and those kind of properties. So that idea actually generalized to topological space. So we define a topological space. So usual notation is tau, or this kind of tau, whatever you choose. So tau is actually subset of a power. So first of all, suppose there is a set X. Let X be a set. Then this tau, it is a topological space. It is a subset of a power set Px. Power set means it contains everything, empty set X and all subsets of X. It is subset of power set and it should have some properties. So we know that if U alpha belongs to tau, alpha is a class, then their arbitrary union U alpha alpha belongs to A, this should also belongs to tau. So it is similar to the property arbitrary union of open set is open. And the second one is if
Excuse me, sir.
yeah.
What do you mean by arbitrary set?
Okay, so arbitrary I want to mean arbitrary union. So here we are not taking union on finite set or on countable set. We can take any set. That is, you can take this A to be a real number. So all those points can be chosen, or any kind of union. So it is not limited to a finite union or a countable union. So you can take arbitrary union over real number, union over everything, whatever element is given here.
Okay, sir. Got it. Thank you.
Oh. So another property is if u1 and u2, two element belongs to tau, then their intersection u1 intersection u2, that should also belongs to tau. If those two properties are satisfied, another property is also there. I have forgotten. So the empty set must be open set, and the whole set X must be open set. So those two things should also belong to tau. If those three properties holds, then we call this tau a topological space. So the whole idea builds on those two things. That is, arbitrary union of open set should be open. So those elements of this tau is called open sets. So it is, the definition seems opposite. In real analysis, first we define open sets and we build some kind of structure. But here, first we define topological space, and the element of this topological space, those are actually called open sets. Okay, so arbitrary union should be there, and finite intersection should be there. So intersection of two things is there means intersection of any finitely many things are there. So this is called topological space. So let me give some example of this topological space. So suppose X be this set 1, 2, okay, subset of natural number. Then if we take this set, for example, let tau 1 equal to this m comma the whole set and this 1. The question, is it a topological space? So we need to see that union should be also there, and the intersection, finite intersection is there. So if we take union of those two things, union of empty and X, this is X, right? Empty union X is X. So this holds, this union is there, and similarly X union 1, this is again X. So union with X will be always X because X is bigger. So you can see that whatever union you take, this also belongs to this tau 1 because X is already there. Okay. Similarly, if we take intersection, so X intersection 1, this will be 1 because 1 is smaller, right? So arbitrary union and finite intersection is there. So tau 1 is a topological space. Tau 1 is topological space. Similarly, if we take the whole set, whole power set, that is, take empty, take the full set X, and if we take 1 and 2, this is also a topological space, right? You can see that union of 1, 2, that is the whole X, and our intersection of 1, 2 is empty. So this is also topological space. Similarly, there are other choices. One can take only empty and only X. Then again, there is nothing to check because union of those two things is X and intersection of those two things is empty. So this is also topological space. Similarly, we can make another topological space. So instead of 1, we just replace it with 2. So this is so all those things are actually topological space in this case. Okay. So a non-example, let me give a non-example. Consider those three things: x equal to 1, 2, 3. So here we can also create non-example. For example, suppose empty is there and 1 is there. Will it be a topological space?
Yes.
There is a slight issue because you can see x is not there, right? X is missing here. X is missing. So if we denote it by tau 4, then tau 4 is not a topological space. Right? Topological space. It is not. Because X is not there. Similarly, if we remove empty set, that is also not. So empty and X must be there. If empty and X is missing, then just discard that option. That cannot be a topological space. Now, similarly, let us try to construct a non-trivial example where empty and X is there, but something is missing. So let us create two examples. Suppose empty is there, the whole set X is there, and now 1 is there, 2 is there, and tau 2, this is empty X already there, 1, 1. Now the question is, are those two things topological space or not?
So for tau 1, it should also contain the union of 1 and 2.
Yeah, exactly. So this union 1, union 2, this should be 1, which is missing, right? 1, 2, this is missing. So by the same reason, so since the union is not there, so this is not tau 1, this is not a topological space. Not a topological space. Topological space. Now what about tau 2?
Intersection of X and the set containing 1, that's just the set containing 2, but then it's not here.
So you can see that if we take the intersection 1 and X, this will be 1, right?
Oh, okay.
So you can check that this is actually, those thing is actually in a ascending order. Empty is containing 1, 1 is containing 1, 2, and 1, 2 is containing X, right? So those kind of situation, in this kind of situation, there will be no issue because union of those two things will be union will be the bigger thing and intersection will be the smaller thing. So if there is such kind of chain, then it will be topology. It will be a topological space. So this is true. This is yes. Okay. So those are a few examples. Now let us define several things. for starting. So given a set X, one obvious candidate will be choose the power set Px, or maybe it also denoted by 2 to the power x. So power set means it contains everything. It has empty, it has, so power sets, it will be set of all sets. So for example, if there are 3 candidates, the power set Px, it will look like the empty set and the whole set and all those kind of subsets. That is, there will be 2 to the power 3 many choice. Cardinality is 3, so 2 to the power 3, that is 9. So empty x, and other choice will be take the single tone sets 1, 2, 3, and take the pair 1, 2, 1, 3, 2, 3, and the remaining one is x, which is there. So sorry, empty x, something is missing. Sorry, 2 to the power 3 means 8, so it is okay. So you can see there are 8 many choices. So again, power set is always a topological space, right? Always a topological space. Top space means topological space. I am writing in short notice. So because empty is there, x is there, and whatever union you take, because all subsets is actually present. So whatever union or whatever intersection you choose, that must be there. So this is always a topological space. This uh, this space is called indiscrete topology. Indiscrete topology. Okay. So indiscrete topology means maximal thing. That is, there is no other topology which is bigger than this topology. It has everything. Okay. It is finest possible topology. And similarly, there is another choice. So take empty and x. So this is always a topology, right? Always a topology. Because union of those two things will be x and intersection is empty. So this topology is called sorry, this is discrete topology. Extremely sorry. Discrete means it has everything, finest topology, and this is called indiscrete topology. Yeah, Sandeep, you are right. So you can talk to me because sometimes I do not notice those chats. Okay, so this is called indiscrete topology. Very trivial. Those two kind of topology are very trivial. It has everything, and it does not have anything other than empty and x. So those are a few examples. Maybe I can write several other examples. So you are also familiar with those two topologies. So in R or R2, you know that topologies are generated by those open sets. That is, a set is called open if there exists for that is, I have already written the definition. So something is called open if there exists open wall around that point which contains that set. So then we call it open set. And this topology, the topology where those sets are open, that is called Euclidean topology. And the corresponding metric for Rn, that is called Euclidean metric. Okay. Similarly, the topology generated by this metric. So again, the same kind of something is open. If instead of this open wall, here we just replace it with P a comma some epsilon or a comma r. Then the topology generated by those open sets are actually called metric topology. So I'm not writing the definition again. So this is called R2, Rn. The topology here, the distance between those two things is given by, for Rn I am writing, that is given by sum of xi minus yi squared to the power half, I equal to 1 to n. Okay, this topology is called Euclidean topology. So here the open set will look like that previous definition. Similarly, for any metric space, the open sets generate a topology. We call it metric topology. It is called metric topology. So you can see that you can compare those two topologies. That is metric topology is same as discrete topology? For example, in this case, Euclidean topology, can it be same as discrete topology? So let me denote it by Euclidean U. Then the topology tau U, that is Euclidean here, Dian. This is strictly smaller than discrete, right? For example, this set 1, this is open set. So let me consider Euclid. Let me consider everything for this R. So R has Euclidean topology, that is usual topology. It is also called usual topology because we always use this thing. So you can see that 1 is not open set in real number. If we consider Euclidean topology, 1 is not open set. But if we consider discrete topology, then discrete means it is the whole set, power set, 2 to the power r, or power set of r, whatever you did. So 1 always belongs to this discrete topology. Similarly, the indiscrete topology, tau I, it is smallest topology. So those are actually called coarser and finer. Definition: if tau contain in tau dash, then tau is called coarser than tau dash, and similarly tau dash is finer than tau dash. Why that is called finer? Because it has more fine pieces. So you can compare those two things by this analogy. So tau dash, it will so compare brick to brick. So here tau dash, it will be like all those pieces by which the brick is made of, and tau is the only whole brick. So tau dash has more finer pieces, and tau has less finer pieces. Tau is the whole brick, but tau dash is all those clay and everything by which the brick is made of. So that is why the name is finer. Tau dash is called finer. Okay. So here we can already see that this power set or this discrete topology is finest possible topology, right? It has everything, and indiscrete topology is coarsest possible topology. Is it clear?
It's
Okay. Okay. What is it? So let me give another example of topology. So consider three element 1, 2, 3, or ABC, whatever. So A, comma B, comma C. So what are all possible topologies on this set X? So we can denote those things by point. Okay, let me count. I don't know. So one possibility is only take empty thing and the whole thing. So we are taking whole thing. So I am denoting it by this boundary. Means I am taking everything. Okay. So this is one topology. Another possibility will be like this. So take only one thing. Okay. Empty. Take, for example, take A and take the whole X. So it is also a topology because you can see those are in a chain, increasing chain, subset by subset relation. So that is also a topology. Another example will be like this. So take this and also take another open set. The type will be like this: empty, whole thing, take A and AB. Again, this is also another chain, right? So tau, tau 2, tau 3, all those are topology. Tau 1, tau 2, and tau 3, all those things are topology. There will be lots of choices. One choice will be like this: take this element, take this AB, and take also this BC. Can you understand from the picture? So tau 4 means empty X. Here I have taken B and those two things, AB and BC. So this is also another choice. So there are several choices. There will be 9 types, and if you count all those things, maybe that can be 23. I don't know, 23 or 29. Sorry. So those are all you can count all those topologies. Okay. So one non-example will be like this. Suppose B is not there. Can it be a topology if B is not there? So if B is not there, then you can see the intersection of AB and BC. So intersection can be shown by the picture. This is the intersection. So B is not there. So it cannot be a topology. Right. So let us solve some problem. Here The question is whether the following is true or false. S is any non-empty set, then and 2 to the power s is the power set of s. Then the question is s belongs to 2 to the power s. Is it true? So this is true. Why? Because 2 to the power s, it will look like empty, and the whole set and all those proper sets, subsets, all proper subsets. So here you can see s is also a member of this 2 to the power set. So clearly s belongs to 2 to the power s. So this is true. Now the question is s contained in 2 to the power s. So this subset notation, it means, so what is the meaning of a subset of b? This means if a belongs to a, then a also belongs to b, right? So the question is s contained in 2 to the power s, is it true?
Mm.
So if this is true, then s should belongs to s, but this is not true, right?
Yes.
For example, take natural number. So natural number means it is 1, 2, 3, etc. So here we can see that 1 belongs to n, 2 belongs to n, but the question is it true that n belongs to n?
No.
This is not true. So s belongs to s is not true. Therefore, um, this is also not true. By similar kind of analogy, that is, s does not contain in 2 to the power s. So this is not true. Now the question is, uh, this set belongs to 2 to the power s. Is it true? So here we can see that s is there, but this s is not there, right? So what is the meaning of this s? This s means we are just cancelling everything. So only this s is there, right? So this, we can see that this thing is actually a subset of 2 to the power s. Okay. So
Sir, can you please explain this again?
uh, okay. So I am saying that if you see there, s, though s is there, s belongs to 2 to the power s. We have observed, but the set here, we are taking a subset of the power set. So if we put a bracket, then this is no longer an element. It is a new kind of thing. Is it there? Can you see inside the bracket this this second bracket is it there? There is nothing like this, because inside the bracket we have only single s, but there is nothing like this. So for example, let me give an example. Let s equal to this 1, 2, 3. So if we put another bracket, then it will look like bracket of bracket 1, 2, 3. Okay. So this thing is actually new. This is not that, those two are different. Okay. So if we put another bracket, that will be a new thing, completely new.
Yes, sir, got it.
Yeah. it is exactly, it is subset of power set. So this is actually wrong. But now this S containing 2 to the power S, is it true? Yes. You have already said this is a subset of power set, so this is right. So that is right. You can also see in this way. So what is a subset meaning? Subset means you cancel lots of things and you take fewer elements. So this is a subset of 2 to the power S, right? You cancel everything other than this S. So is it clear?
Yes, sir.
So that's why sometimes we write in this notation, or sometimes we put equal sign. Those are actually same. Most of the book use this notation, and those two are equivalent. And some people write may not write those two as equal, but most of the book in nowadays, those books consider those two things as equal, same symbol. And if those two things are not equal, we write in this notation. Okay, it depends on the context, so you need to see what they are mentioned. So which of the following are correct? Those are actually preliminary things, that is some set theory and some function maths, those kind of thing. So first one is, f applied on the union is same as f of a union of f of b. So a, b are two sets. Then is it true? F of a union b is, yes. So you can check. For example, suppose we check in this way, right? Suppose x belongs to f of a union b. Means x will look like some a, or x will look like some f of b, right? For some a belongs to a, or b belongs to b. And the first one means x belongs to fa, and the second one means x belongs to fb. Therefore x belongs to fa or fb. Okay, nice. So this is already done in lecture video. And converse is also true. So the reverse exactly holds. Those reverse step also holds. So yeah. So this is true. Now what about the second one? Is it true or not? No. Okay. So let me see what happens. What is the wrong? Suppose consider this function. F sends suppose f is the constant function. Okay. F maps R to the singleton set 0. Everything goes to 0. This constant function. And suppose a equal to the set 0 or 1, b equal to 2. Then what is a intersection b? There is nothing common between a and b, so a intersection b is empty set. Exactly. So if you apply f on the empty thing, you will get the same empty. F of a intersection b is empty. But if you apply f here, so f of a is the same thing. So this is the constant value. Everything goes to 0. Okay. So f of a is the same 0. F of b is 0 again. So fa intersection fb means common between those two things, which is 0. So you can see that this is smaller than this. Okay, so this is not true. This side of equality holds, inequality holds. FA intersection FB is contained in FA intersection FB. And now the interesting thing is that though F does not behave well with intersection, but inverse behaves well. So F inverse also behaves well with union and intersection. So all those three things will be true. Okay, but again this is false. You can create a counter example. Okay. Again, it will be like this kind of inequality. Because what is A intersection B? It means A intersection B complement, and this is same as FA intersection FB complement. Okay. So question number 3 here. F compose G is identity. Then which of the following are correct? So first one is F is isomorphism. So maybe isomorphism is not familiar. So isomorphism means bijection. Those type of thing are equivalent in for set theory. Isomorphism is equivalent to saying bijection, or we also call one-to-one correspondence. One-one correspondence. So the question is, F compose G is identity. Then is F isomorphism? The one answer is no. So let me create an example. So first of all, is F surjective? F is surjective, G is injective. Okay. So those two are true. How can we check? Suppose, how do we check injectivity? Let me check injectivity. Let uh, we need to prove G is injective. So x comma y belongs to x, and we are assuming those. For example, let me denote it by this. So f is a map from x to y, and G is a map from y to z. Sorry, it is opposite. First G, then F. So we are taking two elements from X. Then we want to prove that G is injective. So how do we check injectivity? We assume Gx and Gy are same. Okay, such that Gx equal to Gy. Then just apply F. So if we apply F on the both sides, okay. So there is some network issue. Okay, can you hear me? Uh, is everything okay? Hello. Okay. So G is injective. Similarly, you can check F is surjective, but F may not be isomorphism. So let me give an example where F is not isomorphism. It is easy to write pictorially. So suppose F compose G is identity. Suppose this is G, and so X contains 2 point and Y contains 3 point, Z contains 2 point, and the map F is given by send the first one to first one, second one to second one, and the third one to again this second one. So here you can see that though F is surjective, F may not be injective, right? So F, we are getting that F may not be injective. So this is the counter example. Okay, therefore F may not be isomorphism. Now the third one, last says that if F is invertible, G is also invertible. Is it true? So this is for option B. This is for option C, option A, and for option D. So F is invertible. Given F is invertible, means F inverse exists. So if we apply F inverse on Fg, then this is same as F inverse applied on identity. So this means G equal to F inverse. Therefore J is also invertible, and vice versa. So same can be done with G, because what will be inverse of F inverse? It is F, right? That is F compose F inverse is same as F inverse compose F, which is identity. So F is invertible means G is also invertible, and the converse also. Okay, which of the following are true? The first one says An is this open interval 0, 1 by n. Then what about the intersection? So is the intersection empty or the intersection is 0? Okay, let me see if it is 0 or empty. Yeah. So if possible, assume let x belongs to the intersection. So we are considering the question problem A, option A. So let x belongs to the intersection A, n belongs to n, right? So belonging to the intersection means x belongs to everything, right? Then x belongs to n for all n. And n, it will look like 0, 1 by n, right? That means, yes, that means 0 less than x less than 1 by n for all n. So is it possible? This is not possible, right? By Archimedean property, this is not possible. It is contradiction. It says that nx less than 1 for all n. But Archimedean property says there exists some n for which nx greater than 1. So this is not true. Therefore, x cannot have anything. Sorry, intersection cannot have anything. Hence, intersection is empty. So this is empty, and therefore this is false. Now what about option B? So here n is the closed interval, n equal to this kind of closed interval. Now, now can you say anything?
Contains zero.
Yeah. So in this case, whatever n we choose, it always has 0, right? Therefore intersection n, it is 0. And we also can prove that it cannot have anything other than 0 by the same kind of reasoning. Okay, so this is empty wrong. Now what about D? For D, n looks like this, minus 1 by n comma 1 by n. So what about the intersection n? So you can see that 0 belongs to minus 1 by n comma 1 by n. This is true for all n, right? Whatever n you choose, 0 is, this is true. Therefore 0 belongs to the intersection. For all n this is true. Therefore 0 belongs to intersection minus 1 by n comma 1 by n. So one side it is clear that 0 contain in this set intersection n, and the converse is also true. You can prove in a similar manner. Nothing other than 0 belongs to this set. Okay. So this intersection will be 0. So this is true. So option A and option B. Okay. Is it clear?
Yes.
Okay. Here f is the function given by fx equal to x square. Now the question is, what is f inverse of f0? If we draw, then the graph will look like this. X square means it will be like this. Okay, so this is the graph. Now the question is, what is f inverse f of 0? So what will be the answer? So first we are taking this. Applying it will be like this. So we'll get 0 to 4. This will be the value. Then we are taking the P image again. So the P image will also contain this left hand thing, right? Because image of this thing is also 0 comma 2. Sorry, image of this thing also will be 0 comma 2, minus 2 comma 0. Okay, so let me write it precisely. So we have f of 0 comma 2. It means, so apply f here. So f of 0 comma 2 means all x, all f of x such that x belongs to 0. X belongs to this closed interval. So this is the closed interval 0 comma 4, right? Now we take f inverse of this, f inverse of f02. That means f inverse of this closed 04. But f inverse of closed 04 means all y such that image of y should lands in this 04. But here the function f is defined by fy equal to y square. So y square belongs to 04. What is the, then what will be the answer? So rough y square belongs to 04 means this is if and only if y square less equal to, so 4, and then either y is less than 2, or there is also another choice, or y is greater equal to -2 and bounded up to 0. So that is equivalent to saying 0,2 union -2,0, which is same as -2 to. So these whole things becomes the solution. So is it clear?
Yes.
Okay. Here the question number 6. Again, f of x comma y. This is defined by x plus 1. So f is a map from R2 to R. Now the question is, what is f inverse close 0, 1? So again, let x comma, so the domain is R2, right? So we need to pick 2 points. X comma y belongs to R2. So this is belongs to this f inverse close 0, 1. Okay. So if xy belongs to this, that means f of xy belongs to this closed 0, 1, and that is equivalent to saying f of xy is greater equal to 0 and less equal to 1. And the definition of f of xy, that is x plus 1. So those are actually definitions. So all those steps are if and only. Yes. Therefore option is A is correct. Okay. So list all possible topologies on the set A comma B. Yes, there will be 4 choices. So one choice will be take A and B. So those are A, B. So here we are not taking anything. We are taking the whole thing, that is X, and the empty set. Okay, empty set is always there. Empty set and the whole set. Okay. Another choice will be take the everything, that is empty X, and also pick the set A. So this is our A. So empty X comma A. Yeah. So there are other choices, empty X comma B, and another thing is discrete. Exactly. So we choose A, we also choose B, and everything. Empty X, A, B. So I have not drawn B. This set corresponds to this picture. A, take only B. This is B. So there are 4 choices. So there are 4 topologies. So this is tau 1, tau 2, tau tau 3, tau 4. Okay, my area of research is algebraic topology. So now next question. Question number 8. The first one says, so those are topologies. Tau I belongs to this I as the index set. For example, I can be integer, I can be some things 1 up to n, any other traces. So this is the index set, and tau I are all those topologies. Now, which of the following is or are true? So if those are topologies, is the intersection also a topology? Is union also a topology? Complement of those topologies are topologies or not? So let us see. So what are the properties of a topological space? Defining properties. So tau I are topological space. Topological space. That means empty belongs to tau I. X also belongs to tau I. So x comma empty both are in tau I. This is one property. Second property is for any collection of open set, any collection of open sets U alpha, the union U alpha over this alpha index also belongs to tau. So if U alpha belongs to tau I, then their union should be there. And the third one is for two open set U1, U2 belongs to tau I. This implies that union should also be there. So tau I satisfy those properties. Now the question is, what about their intersection? Will their intersection satisfy those properties? So you are saying yes. Let us see. So first one is empty belongs to intersection of tau I. This is clear, right? Because empty belongs to all those tau i's. If something belongs to all those things, then it also belongs to their intersection. So this is true. Similarly, x belongs to intersection of tau I. So first property is certainly true. Now what about the second one? So let p alpha belongs to intersection tau I. Okay, I am assuming p alpha belongs to this tau I. Then what about union of p alpha? It means p alpha belongs to this tau I for all I, right? So p alpha, by the defining property, the union of p alpha also belongs to tau I. This is for all I. Hence, union of p alpha belongs to, this is true for all I, therefore it also belongs to the intersection. So arbitrary union. So tau intersection of tau I is closed under arbitrary union. Okay. Okay. Now let the third property, let V1 and V2, those two set belongs to intersection tau. Okay. That means V1 belongs to tau I for all I. Similarly, V2 also belongs to tau I for all. Right? Therefore, again by the defining property, if two things belongs to tau I, then their intersections also belongs to tau I. Therefore, V1 intersection V2, that belongs to tau I, and this is true for all I, right? Therefore, V1 intersection V2 belongs to, so it is true for all I, therefore this also belongs to the intersection, right? Hence, this intersection tau I, this is closed under the union operation, so closed under the union operation, and it is also closed under finite intersection operation, right? And X and empty, those two things are already there. Therefore, intersection is topological space. Okay. Therefore, intersection of tau I is a topological space. Now, what about second one? It says union is a topology. Is it true? What about finite union? You are saying that arbitrary union may not be a topology. Okay. What about the finite? Okay. So let us check. Okay. So second one. Consider tau one is that example. Maybe there are 3 points. So I am taking this one, and this is tau one, and I am taking another topology. It is, sorry. So first one is, let me denote it by A, B, C. Then X is again the same set A, B, C. It has 3 points, and a topology on the X, on the space X. It is given by empty, the whole set, and this singleton thing. And tau 2 means empty, whole set, and B. Then so the question, is it a topology? Tau 1 union tau. Yes, this is not a topological space. Just a minute. So you can see that though A and B is there, but union of A comma B does not belongs to tau, which is AB. This does not belongs to tau, right? Sorry, tau 1 union tau. Okay. So therefore, though union of two topological space may not be a topology. Now, what about complement? So this is false. Now, what about complement? So union may not be a topology. Okay, it is given that tau I is a topology. So let me denote it by tau. Tau is a topology. Now, what about complement of tau? Yeah. So, for example, here, if we consider this example, what will be the complement? Tau 1 complement. It will be like everything other than those two. Yeah. Sorry. Yeah. So tau 1 complement, empty is not there, and x is also not there, right? The first defining condition is false, means it is not satisfied. Therefore, tau is tau complement never be a topology, because empty and x is not there. Empty belongs to tau, therefore empty cannot belongs to tau. Yes. Sorry, your voice is I cannot hear. Uh, I can't hear you clearly. Can you write? Okay, you can tell me later. So, question number 9 here, X is infinite set and tau is the topology on X in which all infinite subsets of X are open. So, it is given that X is infinite, size of X is infinite, and it is also given that that tau contains all infinite set. Tau contains all infinite set, infinite subsets. Those are open means it contains all infinite subsets. Now the question is tau a discrete topology or not? So it says that tau is discrete topology. So is it true or false? So we need to see that can we get all those finite pieces also? Can we retrieve those pieces or not? There is some network issue. You are saying yes. Okay, so let us see. So X is infinite set, then we can take two pieces, right? Okay. So the question is, can this be obtained as union or intersection of all those other things? This is the main question. So let X belongs to X. Yes. So let X belongs to X and take A be an infinite set and we are also assuming, okay, a set such that x minus a is also infinite. This is always possible for infinite set. Infinite set can be partitioned into two pieces where both are infinite. Okay. So if we take those two sets, then either a belongs to a, either x belongs to a or x belongs to this another piece. So without loss of generality, let x belongs to a. Suppose this holds. If x belongs to a, then we take this let b equal to x minus a in union the element x. Then what will be a intersection b? You can see that b is complement of a and there is another term which is x, right? So what will be the intersection? Yes, intersection is x. So only common term is x. X is also in a, x is also in b. Other than this, there is no matching. So a intersection b is x. And we also note that we already assume that a is infinite set and x minus a is also infinite. And tau means all those infinite sets are open, right? So since those two are infinite, therefore a is open infinite set. That means a open, and this is infinite. That means x minus a is open. Now intersection of two open set is open, right? Definition of topological space. Therefore, intersection is open. Since this is intersection, this is open set. And it is true for any x. For any x, this is open. This is open for all x belongs to x. Hence, whatever set you give me. So suppose you give you have given me a set. Suppose K is a set from X. K is a subset. It can be written as those Ki, right? K can be written as those Ki. I belongs to R, right? And this is same as union of this Ki. Union of those singleton set. And union, we have already seen that singleton set is open. Therefore, union of arbitrary union of singleton set is also open. Since arbitrary union of open set. So here we have proved that singleton sets are open here. Sets are open. And now we can see that any set, whatever subset you give me, it can be written as arbitrary union of singleton set. And arbitrary union of open set is open because tau is a topological space. Therefore, we can see that any subset belongs to the topological space, right? Let K be a subset, then K is from here we get K belongs to tau because K is open. Hence, this is true that this is discrete topology. Tau contains every subset. Is it clear?
Yes.
Okay. So here Yes. Hello. Okay. So X is infinite set here, and tau contains empty or all subsets of X whose complements are countable. So here tau is defined as empty sets or some set U such that complement of U is empty. Okay. Sorry, complement of U is finite, countable. Now the question is X comma tau, is it a topological space or not? Is this a topological space? So let ui or u alpha belongs to tau. Okay. Then we need to prove first. Can you see that empty set is there? By definition, empty is there. Can you see that the whole X is there? Because what is complement of X? Remove X from X, which is empty. So complement empty set is always countable. So X is already there. So those two things is there. Now we are assuming U alpha, those are there. Okay. Alpha belongs to some index A. Now what about union of U alpha? So U alpha is there. So U alpha can be empty. So we are ignoring those empty things because taking union with empty gives empty. So I am assuming U alpha complement another thing, that is complement of U alpha is countable. So U alpha complement is countable. This is without loss of generality because if we take union there is no issue. Now what about now observe this fact. What about complement of this U alpha? Yeah, intersection of the complement. This is by De Morgan's law. And we know if something is countable, if we take an intersection, then that will be also countable, right? U alpha complement is countable. Right? Therefore,
Excuse me, sir.
yes.
Is this true for any arbitrary set, even if alpha is uncountable?
Yes. Because note that U alpha complement, if you take intersection, that will be subset of U alpha, right?
Yes.
This will be subset of any U alpha. And subset means its size always reduce, right?
Yes.
Therefore, if we take intersection, that will also be a countable set because it has smaller size, smaller or equal size, maybe finite or maybe countable infinite, right?
Yes, sir. Got it. Thank you.
So complement of this union is countable. This is countable. We have arrived in this conclusion. So by definition, therefore, union of U alpha belongs to tau because this is defined in this way. If complement is countable, then that should be there. So here complement of this is countable, so that must belongs to there. Okay. So union of U alpha is there. There is no issue. Now we need to see about the union. So let u1 comma u2 belongs to tau. Okay, then again we can assume that none of these are empty, because let's such that u1 and u2, those are non-empty set. We have again, that is, here also we have, without loss of generality, assume u alpha, those are non-empty. We can always assume, because union and intersection for those, the check is obvious. So we can assume this is non-empty. Then this belongs to tau and this is non-empty. That means complement of u1, that is countable, right? And complement of u2 also countable. Therefore, union of two countable thing is also countable, right? Just rearrange the same thing. For example, we know that so u1 is countable. That means you can write u1 complement is countable. You can write it as x1, x2, x3 dot dot. So that will continue. Similarly, u2 complement is countable, means you can write it as a sequence y1, y2. Then you just reorganize. So u1 complement union u2 complement, just rearrange those two things. So first you write x1, then you put y1, then x2, y2. Yes. So that will also be a sequence. You just rearrange those two things. So you will get a countable thing. So u1 complement union u2 complement, that is also another countable thing. But note, this is same as by De Morgan's law. This is same as u1 intersection u2 complement, right? This is, those two are same. This is countable. And again, this is the definition of tau. Tau contains empty set or something whose complement is countable. So since the complement of this thing is countable, therefore u1 union u2, sorry, u1 intersection u2 belongs to tau. Hence we are getting tau is closed under arbitrary union and finite intersection. Therefore, tau is a topology. Okay. Yes. So this kind of topology is called co-countable topology. Okay. We are putting the word co because we are taking complement. So this is actually called. This is called co-countable topology. Similarly, you can just replace the word countable by finite, and you can check that also form a topology. Okay, that is called co-finite topology. Okay. So now the second question is, what happens if x is countable? So can you explicitly describe tau? What happens if x is countable? Yes, yes, Sandeep. You previously attended this. Nice. So, can you guess what if x is countable? Exactly, exactly. You are right. So, if x is countable, we'll get discrete topology. Why? X is countable Then take any finite set. So whatever set you choose, that complement of that thing will be countable, right? So let u belongs to maybe blue color. Let a belongs to x. Sorry, a is a subset of x. Then complement of a, this is countable, right? Because complement of a is strictly its size will be smaller than this x. So subset of a countable set means it is countable. So a complement is countable, right? Since a complement is a subset of x. Therefore, from here it is clear that, so we are assuming again a is non-empty. Again, if a is empty, there is no issue. So every subset belongs to, since a complement is countable, that imply a belongs to the topological space. Therefore, every subset belongs to tau, right? Therefore, tau is actually the power set. Okay, I will include later. So tau is the power set. Therefore, in this case, if x is countable, then we are getting the same discrete topology. Discrete topology. This topology is called discrete because everything is there. Now, question number 11. The first one is topology tau. Okay, so tau is, so we are considering a topology on R2. So we need to prove this is a topology. So let me draw this pictorially. So empty set is there, the whole set is there, and other sets are given by this equation x comma y, which satisfy the property x greater than y plus k. So for example, suppose k equal to 1. For k equal to 1, we get this line. This is x greater than, x equal to y plus 1, and therefore x is greater than y plus 1, that will be given by this half, this lower half. Okay. Similarly, we can draw other things also. For example, x equal to, this area is x greater than y plus 1. Similarly, x by parallel line we can draw this side, that is x greater than y plus 2. X greater than y plus 1. Okay. Now the question is it topology? Can you easily see if this is topology or not? So there will be no issue with those R2 or empty. The question is, can you see that arbitrary union of those region that also belongs to this tau? Can you see that?
Yes.
For example, if you take this G1 and if you take this G2, what will be there in union? Yes, the union will be the minimum thing, G1. Similarly, you can prove that arbitrary union of this Gk, K is any index, that is G infimum of this K. So let me write K belongs to this set K, infimum of small k such that k belongs to this indexing set. Okay. So for real number, infimum always exists, right? This is example, and this is, you can prove that. Just prove this fact. You can easily prove. From picture it is clear. Just use this idea, first prove this thing, and using this idea you can easily prove this fact. So infimum over real number, k is a subset of real number. So real number is complete, that is infimum and supremum, that if exists that belongs to real number. So it can be infimum can also be in negative infinite, but there is no issue. Negative infinite means it will give the whole plane, whole R2. That is, shift everything further back. So you will get whole R2 plane, right? So this union will be either R2 or it will be one of this GK. Infimum, it will be some real number. For example, so it has two choices. Either it will take some from GK0, K0 is real number, and another choice will be minus infinity. But G minus infinity is not defined. This is actually R2. So this is abuse of notation, but it will be R2, the whole thing. So R2 is also there, and GK0 is also there. Therefore, it is closed under arbitrary union. So there is no issue. Now, what about intersection? G1 intersection G2. So this is our G1 region, x greater than y plus 1, that is G1 region, and this is G2 region. So what about their intersection? So instead of 1, 2, I am writing K1 and K2. That will be G of maximum of those K1, K2, right? Maximum or supremum, whatever you write. Supremum of this K1, K2. Okay, so this always takes this kind of form. So this belongs to tau. This is also belongs to tau. Therefore, tau is a topology on R2. So tau is a topology on this plane. Now the question is tau a topology on R2 if K belongs to R replaced by N or replaced by Q? So what will be the problem? So if K belongs to N, so instead of those any real number, now those are only integers. That is, this thing is integer. So those are actually drawn for integer. So this is given. Now what can you say? For a natural number, there is no issue. Because again, whatever you take, minimum of subset of any natural number, infimum of a subset k is natural number, k is a subset of natural number. This is for case 2. This always exists. Always exist means there is no negative infinity problem also. So it always takes this kind of form. Just take the least number. So natural number always admits lowest bound, lower bound, whatever you call, greatest lower bound, GLB. So natural number, whatever set you pick, that admits infimum. So again, the same, this will hold. That is that G infimum, that will be belongs to tau. Either there is no, this case will not arrive. So we'll get this kind of thing where K0 belongs to natural number. So for natural number, this is okay. In this case, tau is topological space, top space. Now what about K belongs to Q? For this case, this is the case K belongs to N. Not. Okay. Why not? Yes. This is not a topology. Okay. So for example, yeah, you know that this kind of limit, so this limit, what is this limit? 1 plus 1 by n to the power n. Yes, this limit is n e, and if we replace by minus 1 by n, this limit is 1 by e probably. So in this case, this is actually a decreasing sequence, and you can see that infimum of this set. So take K be the set. Yeah, K be the set. This 1 minus 1 by n to the power n, where n belongs to n. In this case, so clearly this is a subset of Q. There is no issue. Those are rational number. Now the problem is infimum of this K. This is 1 by e. This does not belong to Q. Therefore, uh, this limit, this union of GK, which will be of this form. So therefore, the problem is like this: union of GK, K belongs to big K. So this is small k actually. This is some G1 by E, but we have not taken any G1 by E. In this case, this K belongs to the rational thing. So there is no G1 by E. If we consider K are taken from rational. So is it clear that union of this does not belong to tau in this case?
Yes.
Okay. Any question? Sorry, your sound I can't hear. It's too low. Okay, so this is not a topology because it is not closed under arbitrary union. Prove that R2 comma tau, this is the topological space where tau are empty or complement of finite sets of lines and points. So the question says the topological space tau, or maybe this tau, I always write this notation. So here tau is empty, or another choice is u. So u takes this form. Complement of u, this is finite sets of lines and points. Okay, so this means U may look like this. So U may look like everything other than this line. So U is everything other than this thing. So this is one choice. Another choice will be like this. U is anything other than this origin. So except origin, take everything. So those are choice. So this is one example. This is another example, and there can be combination of those two things. You is just remove a point, remove a line. So those are choices of U. Now the question is it a topology or not? So it is topology. It is already given. Now how do we prove that? So what about intersection of those two things? MT is there, R2 is there. There is no issue because finite complement of finite thing means you can take nothing. That is, nothing is also finite. It has size 0. So complement of finite sets of line and points, you may not take complement of anything. So you will get the whole R2, right? So R2 is there and MT is already there. So now we need to check that arbitrary union and finite intersection is there or not. So what about finite intersection? For example, in this picture, intersection of those two things, what will be there? If you intersect those two things, you will get the same picture because it has less number of points. Okay, so you will get the same thing. For example, there can be other choices. Uh, this is one topology, one open set. Suppose this is U1 and another U2 will be like this. U2 is another diagonal. So just remove this line. Okay. Then their intersection is given by removing those two lines, and their union will be given by just remove this point, maybe where the intersection. So just remove this point. So this also belongs to this case because removing a point is also okay. So you can check this forms a topological space. The argument is very easy. Just see what happens when we take complement. It is just application of De Morgan's law. You only need to see that two line. So you only need to see this fact, that is finitely many lines intersects in points, in finitely many points. So this is the fact you need to use to prove that those are closed under arbitrary union. So by this fact you can prove this is a topological space. Again, the same De Morgan's laws application. Now I have only 5 minutes, so let me skip those problems. So again, this is interesting problem. Here, the topological space, it has only 4 sets. One is X, empty, and 2 sets, A, B, which are non-empty and which are proper subsets. Means it cannot be X itself. Now, what condition must A and B satisfy? So, first, let me split into two cases. So, let case 1, A intersection B is empty. Okay, in this case what happens, if their intersection is empty, then their union should belongs to tau, because tau is a tuple. Okay, so their union belongs to tau. So what are the choices? Then sorry, uh, someone's okay. So union
Sir, A
belongs.
union B should be X.
Sorry, Sandeep, please. Okay. So union belongs to tau means,
Sir, A union B should be X.
yeah, there are four choices, but the problem is A union B cannot be empty. A union B cannot be A because they are disjoint. So A union B will be something plus other points. So the only choice is, this is because tau is topology. Tau is a topology, and A union B belongs to tau means A union B is X. So from here, it is clear that AB forms a partition. So pictorially, this is X, and those two are A and B. This is A, this. Okay, so that is uh, saying, using those two property. Those two properties says A B is complement of. So this condition must hold in this case. Okay, that is I just keep that question. So this is the question. I can show it later. It will be in the slide, so you can see. Now case 2. So another case is A intersection B is non-empty. So then what are the choices? Can A intersection B be X? Is it possible? This is not possible because A and B are proper subset of X. Right? So A intersection B, there are two choices. A intersection B is A, either this hold, or A intersection B equal to B. So in this case, we get a chain. So in this case, we get a chain like this, empty, then A. Uh, for first one, in this case, we get a chain empty, which is contained in A intersection B is A. That means B is smaller, right? That will imply. Those are strict equality inequality,
Sir,
and
A is smaller.
sorry, A is smaller because we are taking intersection. Thank you. So the second one, A intersection B equal to B, that means B is smaller. So those three kind of relation can be obtained depending on the condition. Okay, those are few questions here. You can solve on your own because I have already told. Okay, again the same kind of question. A q, it is given by q comma infinity. Q belongs to rational. Now we need to show tau is not a topology. This is the same issue, right? You can take q maybe denoted by qn. Take qn to be 1 minus 1 by n to the power n. Then you can see that union of aqn. So here n belongs to n. This is actually a 1 by e, because this converges to 1 by e. Okay, so just see the picture what happens there. So first one is, for example, if n equal to 1, then we will get 0 to infinity. Okay, then the second one will be like this. Oh, sorry, I'm making some mistake. It is not union. I need to take 1 plus 1 by n, because for union it will be like this. So here I need to take 1 plus 1 by n, which converges to e. No. That is wrong. Something from the negative number. Means the union should converges to here like this. So something I need to create a decreasing sequence, which yes, which is not. So I need to take a decreasing sequence which converges to this left side. So maybe I can take this sequence is increasing. So if we put negative sign, that will be decreasing. Okay, now that is okay. So in this case, it will converges to a minus e, but a minus e does not belongs to tau, because what is by definition a minus e, it will look like minus e comma infinity, but minus e is not allowed because q belongs to the rational, e is not rational, so this does not belongs to tau. Okay, so
Sir,
yeah,
sir, by this method, can we not say that this is not topology?
yeah, this is not topology because arbitrary union of open set is not open in this case, right? Though
Sir,
AQN,
if we take sir intersection of sir 0 comma infinity and 1 comma infinity, sir, then intersection does not belong to this topology.
0 comma infinity intersection 1 comma infinity, but in this case intersection will be 1 comma infinity, right? So using this fact you can,
Yes, sir. Yes.
okay. So you just check my step, there can be some mistake, I am not sure, but this is the whole idea, that is you need to create a sequence which is decreasing and converges to some irrational number. That is the key issue. Okay, there are several questions, but I am not solving those questions. So let me stop here. And if you have any question, please feel free to ask. Oh, I will share today. Yeah, I'll share those slides. Do you have any question? Okay.
Sir,
Yeah.
I have further sessions like this.
You have further session?
Will there be more sessions like these? Maybe in the upcoming weeks and months?
Yes. In upcoming weeks, that is, in each week, Friday at from 6 to 8.
Okay, sir. Thank you.
Sorry, what are you telling, Sandeep? Okay, you are welcome. Yes, I'll share those questions. Okay, if you have no other questions, then let us leave. Thank you for joining.